Hi, welcome to Calculus 3. We are going to start this semester by taking a look at surfaces in 3 dimensions. Let's go see what this interesting story looks like. So today we are going to have a brief overview of this section in chapter 8, surfaces in 3D. I have listed some of these that are presented in this section, and I've listed them in order that I think are the easiest for you to follow. You remember the story of curves in Calculus 1 and 2. It's quite an interesting and sometimes complicated story to tell. And of course, we expect the situation in 3D to be much more challenging. So for today, we are just going to have a general lecture for looking at these things and their pictures, and then we are going to postpone the mathematical calculations to the next lecture. Okay, I think the simplest surface for everybody is cylinders. Of course, cylinders, you know, the basic example of it would be just a can. Cylinders that we have in mind are going to be a bit more general than that. Essentially, any curve that you take and then draw parallel lines from points on that curve, you can create a cylinder. But we are going to come back to that issue later on. So the formula for a cylinder is going to look like a formula for curves that you have seen in Calculus 1 and 2. Next up is a story of spheres. Spheres, the formula looks like a distance formula from college algebra, only that now we have 3 coordinates to watch out for, and of course a basic example of it would be just a ball. Planes, the equation for the planes looks like this linear equation, and a basic example of it would be like a section of your roof. Typically your roof is made from several planes. Next up in the list of complications perhaps is surface of revolutions. Surface of revolution, the basic example of it will be like a vase. Then we come to something that is a bit more complicated in its variety than the ones we have seen so far, and those are so-called quadratic surfaces. Quadratic surfaces is a polynomial of degree 2 in 3 variables, x and y, z. So the full form of it, you see, has 10 coefficients, and that is pretty crowded. To be able to manage to say something but not get too bogged down in the issue, we are going to assume some simplifying facts. One of them is that the surface is in some sense parallel to the axes we have. That's going to make the middle 3 coefficients to become 0, and that makes it that much less crowded. Next, we are going to assume that the picture is, if it has a center, the center is at the origin, and that's going to make the problem substantially less crowded. It's going to look like a sum of x squared, y squared, and z squared equal to some number, say. If the picture doesn't have a center, then the equation boils down to something looking like perhaps this one, like a z is equal to x squared plus y squared. The shapes that we are going to take a look at that fall under this umbrella of quadratic surfaces are divided to a variety of categories. One is shape of the ellipsoid. This is a example of equation of ellipsoid. I just put some numbers for a, b, and c, and k so that we have an easier way of looking at them. All of these are positive. A basic example of that would be the Earth itself or football. These are 2 approximations for what this shape looks like. Hyperboloid of one sheet. One of these signs is negative. As an engineering example of it would be a cooling tower. I'm going to show you many more examples. Hyperboloid of 2 sheets. 2 of these signs are negative. We are always taking the right hand side to be positive. I haven't found that many examples of this thing showing up in engineering, perhaps just one. Next up, if the right hand side is 0, we have so-called elliptical cone or a double cone. This is an example of a formula for elliptical cone. For shapes that don't have a center, the equation turns out to boil down to something like this. And we have two types. One is so-called elliptical paraboloid, z is equal to sum of these two, and hyperbolic paraboloid with z is equal to the difference of these two. Example of a hyperbolic paraboloid would be the satellite dish that's probably on the roof of your house. An example of a hyperbolic paraboloid, something that looks like a saddle or sometimes a snack like chips or something, that also has at times a shape looking like a hyperbolic paraboloid. Now let's go ahead and take a look at these things just so that we know these things actually exist out there and they're not just mathematical fabrications. So we talked about of course surfaces of revolution. Surface of revolution, we take a curve and rotate it around some axis, and you have seen plenty of problems like this in calculus 1 where you are asked to calculate perhaps the volume or something like that, perhaps maybe surface area. Well, that's what the surface of revolution looks like. A vase is a very good example. Next up, we talk about ellipsoid. A big example of an ellipsoid would be Earth itself. Here's a picture of it. It's an exaggerated picture. The story is that if you want to think about Earth as a sphere, you notice that the radius going to the equator is a bit longer than the one that goes to the pole. The difference between the two of them is about like maybe 13 miles or something, compared to the average radius of Earth that is about 4,000 miles. That's a tiny difference, less than 1/3%, but it's an issue for anybody who deals with GPS and so on. So that's what an ellipsoid looks like. Earth, or an exaggerated example of that would be a football. Next, we talked about hyperboloid of one sheet. This is perhaps the structure that shows up in a very prominent way in so many different places. Somehow cannot miss it. Here are some examples of this. This is an old one. This is perhaps more recent. This is an example of, again, hyperboloid of one sheet. This is an extreme example. This is an interesting take on it. Another one, it's a piece of it. Another one. So as an engineering example, some of the cooling towers that you see are in this shape. If you are interested in architecture, the work of Antonio Gaudi probably is going to catch your eye. He has a lot of elements in his architecture that are based on these quadratic surfaces. All over the place you see either hyperboloids or paraboloids and so on. So something, if you are interested. As I said, the only example I found where there is a hyperboloid of two sheets, it would be a reference in one article. And then what if we want to experiment with our formulas? What do we do? Of course, we are going to learn how to do this thing by hand. We want to train our mind so that we can kind of see the association between the elements of a formula and the shape of that formula. And then we can always go to some software to make sure that our perception is correct. A nice one is this example. Let me start with what we had. So here I'm entering a formula. 2x squared plus 3y squared plus 4z squared is equal to 5. and this is the graph that it produces. The graph is not very refined, because if I increase the number of points on it, my computer is going to slow down quite a bit, and we don't want that. So when you are practicing at home and you have a computer better than what I have, then sky is the limit for you as how many points you want on your picture and such, but I am using some small numbers. Okay, so we said this is the ellipsoid, just like the Earth. Depending how different these three numbers are, you can't move away from a sphere as much as you want. Then we said hyperboloid of one sheet. Hyperboloid of one sheet has 1 minus here. So you change your formula and press return. And you notice this shape. There's a hole in the middle of it. And the ones that we saw in those architectural examples, typically like half of this thing. The hyperboloid of two sheets, if you have two minuses here, press the return. Hyperboloid of two sheets made of two pieces, kind of like cones, but with rounded corners. Then we had elliptical cone. Elliptical cone, we had 2 plus 1 minus, and the other side is 0, or you can have up to 2 minus and 1 plus. And then let's press the return. And this is an example of a cone. Again, the cone looks rather jagged because the number of points I have is rather low. Again, at home you go up to 100, as much as your computer can allow. Okay, then we said that we have something called elliptic paraboloid or hyperbolic paraboloid. These are the shapes that don't have a center, so we are kind of looking at them from one extreme corners. Let's write one example. So if I have z is equal to, say, x squared plus y squared. Okay, so this is, you see, it looks like a cone, but at this tip of it is actually round. This one will have a circular base. If you have used two different numbers here, like 3 and 5, then you get a kind of a paraboloid, where when you cut it, you have the cut looking like an ellipse instead of a circle. If the sign between the two of these is negative, then what we get is, I don't know if you see this thing well, it's like a saddle. So that's where you're going to be sitting. Not very comfortable saddle looks like, but that's the idea. It looks like a saddle. Okay, so what we want to do is just practice with these things in a mathematical style and get a sense for them, so that we can use it in a variety of other problems. Perhaps we are going to be asked to calculate the volume or center of gravity or this or that, and we need to have a perception what the actual shape looks like. And again, we want to train our mind to become familiar with the formulas and be able to produce the picture in our mind. That software is just secondary to help us along, but we don't want to delegate everything to that software. Okay, in the next lecture we start with some details here, and then work our way through some examples and see how we can learn this topic. Until then, good luck and God bless.